So today what I'll talk about is GANs, Generative Adversarial Networks, which is one of the most exciting innovations in this area of generating cool new images, especially images that are mixtures of things that didn't exist before, right? And so we're going to have basically 3 lectures on GANs, and today is just basically the intro lecture. What is it? What is the basic idea? And then on Thursday, we'll get into more advanced versions of GANs. And then on Monday, we'll get into even more fun versions of GANs. So basically, this is just like the very beginning, okay? So GANs, which stands for Generative Adversarial Networks, were proposed initially in 2014 by Goodfellow et al. You're not seeing what I'm saying? Gotcha. And so these quickly supplanted VAEs as the preferred method of image generation, right? Now, like we talked about before, VAEs themselves are not awful, right? I mean, like VAEs kind of form the underlying basis in some sense of the first version of DALL-E, among other innovations, right? But generally, GANs resulted in things that were more interesting for artists to learn about, for neophytes to tweak. But I will say up front that they're also a little bit harder to train going in, okay? So the basic idea, and I'm sure that some of you are already familiar with this, is that we have kind of 2 adversaries that are trying to compete to do a good job, right? So we have 2 adversaries. We're going to have a block called G, which is the generator, and a block called D, which is the discriminator. So the idea is that G is going to try to take random noise and convert it into images that look like they were drawn from the desired class, okay? So basically, G takes random noise, and their output is hopefully going to be an image that looks like the training data. And D is like a classifier. It's going to try to predict whether the image that it sees as input is a real image that came from the training data or a fake generated image that came from the generator. So basically, this is like a classifier. Is the input image real or fake, by which we mean generated. And so these 2 goals are in opposition, right? The generator wants to do a really good job making images that look like they came from the training data. The discriminator also wants to do a really good job trying to tell the real images and the fake images apart. And so we try to make both of these images better, or both of these networks better and better, until at the very end, the generator is doing a great job in making images that are fooling the discriminator. And so it's a little bit of a dicey thing, as I'll talk about, like how do we train these 2 networks separately in order to converge, okay? So this also is kind of like an introduction to one concept that is going to become more used later on, for example, in diffusion models, which is that the idea is that instead of the latent space, which we talked about for VAs being just like a vector that we choose in this embedding space, here the thing that's controlling the image output is going to be a random noise input, okay? So the latent vector is really just a vector that's drawn from random noise, okay? So let me just kind of write down what I said a little verbally. So initially, basically, at the very beginning, G just produces random noise. And D is basically a coin flip, right? It doesn't know whether things are real or fake, okay? And we want to alternate training these 2 networks to both get better. So the 2 networks to get better and better. So G has to work harder to fool D, and then D has to get better to tell things apart. Okay, so I'm being, very vague about what the network architectures of G and D are, because really they can be anything that serves a purpose, right? Like D could be any classification network, and G could be any generative network, right? So that's why I'm being super kind of hands-off about exactly what the structure of G and D are, because this is the fundamental thing that defines a GAN, is this two adversarial networks working against each other, right? But there's nothing about a GAN per se that defines what the structure of those networks are. And there are zillions of different kinds of network structures, okay? And so the first one that we talk about, this is the one that is first introduced in the book, and it's kind of the first kind of productive image GAN, was what's called the deep convolutional GAN. Or DC GAN. And this was by Radford et al. In 2015. And so here, basically, D is D and G are both deep convolutional networks, basically. And D is a classification problem that outputs a number in the range of 0 to 1, where 1 is real and 0 is fake. Okay. So let me just be a little specific. So in this case, G input is a normal 0, 1 length 100 vector of IID noise samples, and the result is an output image. And I don't remember exactly what the original dimensions of the output image were, probably something low like 64 by 64, right? We'll talk on Thursday about ways of, again, scaling the output of the GAN image up. But just like for the VAEs, you may find that to run your own code, you may have to significantly downsample your images to get something going, okay? And then D is basically just like a, deep CNN that results in a 0 to 1 probability, more or less, where 0 is fake and 1 is real. Okay, so same kind of idea where we've got this latent space where we can explore. We'll talk about this a little bit more next time. And so let's talk about, kind of how the training process for this kind of network would work, okay? So, to train D, what we would do is basically we have some sort of fixed generator, right? So noise vector comes in. We have a G that, for the purposes of this step, is fixed. And then this produces a fake batch of data. Kind of in parallel, we have a real batch of data that came from your training samples. And we put these into the discriminator that we're trying to train. Ideally, so this is going to produce some outputs like, 0.1, 0.3, 0.2, whatever. This is going to produce some outputs, 0.8, 0.9, 0.7, whatever. And I'm trying to drive these numbers to be equal to 1, and I'm trying to drive these numbers to be equal to 0. And so you can see that there's kind of a natural loss function that comes from binary cross entropy, which is what we talked about before, right? So the natural loss is the binary cross entropy cost function. And so let me write this more explicitly. So this is like saying that we want to have averaged over all of our data So let me write this down first, and we'll talk about what it means again. So here, this yi is the ground truth, 0 or 1. And this p is like the prediction of the discriminator, which is a real number in the range 0 to 1. Okay. And so for every given sample, only one of these terms is active, right? Because either the truth is 0 or the truth is 1. Okay. And so if we want these things to match up, then when when this is good, the loss is really negative, right? And often you see this written in a different way, right? So in a slightly different way, kind of decoupling these two terms, you see it written like this. I'm trying to minimize the expected value of the log of d of x, where this term is basically the truth term, right? This is like saying, the actual sample is real, and the d acts on some real sample x, right? So in some sense, what I want to do is I want to have the expected value of the discriminator output of the truth. And then I have z here. Z is like the latent space, right? So it's like I sample something from the noise vector. And this is the case where this is fake or generated data, where yi is equal to 0, and then the d is acting on a generated sample, which comes from pushing that latent noise through the generator. And so in some sense, d and g are trying to play this adversarial game, right? So d wants to minimize this, right? D wants to be as good as possible on getting the labels correct, okay? And G wants to maximize this, right? G is trying to fool the discriminator into thinking that this term is not what it should be, right? So this is often called like a minimax problem, right? Because D wants to minimize. So let me just kind of say it in a different place. So here, D wants to minimize this, and G wants to maximize this. So in some sense, this is like the key equation for training the GAN, okay? And actually, since I kind of started with talking about what is the, D training process, the G training process is basically also kind of the same kind of thing, right? So in the G training process, there is no real data to worry about. All I'm trying to do is generate, or there is no discrimination problem, right? All I'm trying to do is generate data that the discriminator thinks is good, right? So training G is like saying, I have noise, I put that through the G, now I'm able to change the parameters of this. This produces a fake batch of data. And what G wants to do is to put this through the discriminator, which in this step is fixed. And the discriminator is going to produce a bunch of values, which may be kind of in the middle somewhere. And what G is trying to do is it's trying to force those values to be 1, right? And this then leads to a loss, right? So this is kind of equivalent to fooling the discriminator, right? That's what G is trying to do. So G is trying to make images that D thinks are real. And we have to alternate the D and the G training steps, otherwise the whole thing doesn't really work. So, it's a little bit of a black art to decide, like, how many steps of G do I do before training a D step and so on, right? So for example, if I didn't do this all at once, I could build a very weak discriminator that would be super dumb, and it would just think that everything that G made was real, right? It just could output 1 for everything, right? but then that wouldn't be a very good discriminator, right? So training is kind of like a fight for dominance between these two kind of separate neural networks, right? So, training, is a fight for, dominance, because G and D have opposite kind of goals, right? So typically by the end, the discriminator is pretty strong, but on the other hand, at that point, the generator is also really good, right? And so typically what happens is you train, and then at some point you're left with a really good generator, and you throw away the discriminator because it's not important for your, for the rest of your problem, okay? So that's kind of like the basic principle, okay? Now, training is hard, right? And again, until you start to do it, which I'm going to ask you to do on homework 2, it's difficult to kind of get an intuition for how it should work, right, or what you should change. And so I'm sure you could find lots of practical advice on how to train a GAN, right? But let me just say, what are some of the problems that you might see, right? So training is hard. And there are a bunch of things that can go wrong, right? So one thing, for example, is that the discriminator overpowers the generator, meaning that D gets to be too good, and then improvements that you try to make can't trickle back to the G. Right? So once the D is so good, then the G has no idea how to improve to make the discrimination, to make it better, right? Conversely, you could have the generator overpowering the discriminator. And what's happening there is that G could basically trick D on a very small sample of really nice images, right? And so basically the generator is always making the same great images, and the D says, oh yeah, I think all these look pretty good. The problem is that there may not be a great diversity of images that's generated by G, right? So this is like saying that G can trick D on a small set of good outputs. And so this is sometimes called mode collapse. For example, I could map every point in the latent space to the same great output, and D would think, oh, this looks great, right? But I'm not really learning anything. I'm not having any sort of diversity in the outputs, right? So basically, there's no diversity in the outputs. And that kind of gets back to, we talked about image quality metrics at the end of the last lecture, right? One of the ways in which you evaluate a GAN is by looking at not just how good the images are, but whether they can generate a wide variety of images, right? So you don't want to be in this mode collapse scenario. Okay. So what else do I want to say about this before I open up for questions here? Well, one thing that's also kind of tricky is that normally if I'm minimizing a cost function, I kind of know how well I'm doing, and I can plot I can plot some sort of decrease in the gradient, decrease in the cost function, for example, right? But in this case, it's hard to monitor training since basically the G and the D networks are constantly changing, right? So these loss functions are always kind of implicitly changing, right? If I do my G cost function and I suddenly change the D network, then maybe a value of -8 in my cost function is not directly comparable to the value of -8 for the new discriminator, right? So I can't necessarily watch a curve that goes down and down and down over time. Sometimes I'm going to have a curve that seems to kind of like jump around over time, and so it's not easy to necessarily set a stopping criterion automatically. I think what happens a lot of times in practice is that you kind of keep on training your GAN, you look at the losses, but you're also looking at generated pictures along the way, and you kind of stop your GAN training at a point where the pictures look okay, more or less, right? In fact, it may be that by the end of your training, the loss function for your generator is actually going up according to whatever the discriminator is doing, but the images are looking better and better. So it can be a little bit counterintuitive, right? It's not like minimizing a single loss. So it's, not like, some sort of decrease over time, but it's probably something that more looks like, something bursty like this, and maybe it goes up at the end, right? So it's not quite the same as some sort of normal gradient descent kind of problem. And then let's just say that there are tons of hyperparameters to investigate and tune. Right? Because I've got fundamentally two independent networks that I'm training, and I have to make architecture and parameter choices for both of those networks. And there's like, all the things that are problematic about training one network, suddenly I have the problem of training two related but fundamentally separate networks, right? So for example, just as an illustration, I did try training, and this is an example from the book on a DC GAN, right? So actually, I know there's one group that was talking about doing Legos. Are you guys doing Legos? So this is a Lego data set, but it failed, right? So if I look at the example, these are like grayscale pictures of Lego blocks, which I think actually are more like rendered pictures than actual pictures. They build this GAN, it's a bunch of convolutional layers, right? And then, you start running it, and, it looks okay in the beginning, right? It's kind of like, first it generates stuff that doesn't look like a Lego brick at all, right? And it's kind of like a noisy image. And eventually, it doesn't take too long before it starts generating like blobs. And actually here is probably a place where I'm not exactly sure what the parameters are, but to me this looks like something where, the generator is improving, and then I change the discriminator, and there's kind of like a step change in what these images look like, and then I get a little bit better, right? And so this process keeps on going and going and going. But ultimately, if I look at the outputs, I can see that at some point, something has gone wrong in the training. So if I scroll down a little bit more, like after many, many epochs of training, I can see that these kinds of things give me some sense that things have gone wrong, right? So it says that the real accuracy is 0 in the discriminator, the fake accuracy is 1, the discriminator, the accuracy overall is 1/2. So it seems like something has gone wrong, and this discriminator isn't learning anymore, and the images themselves don't look any more like Lego bricks the more and more I train, right? So I'm no GAN expert. I don't know exactly what to do to fix this GAN to make it better, but I can see that it didn't work, right? So I'm sure that when you try to train your own GANs, depending on whether you try to do it yourself versus use a off-the-shelf thing, you may come across these same problems. But on the other hand, I wouldn't necessarily recommend that you use this particular GAN, right? So let me show you another GAN that actually seems to do better right out of the box, okay? So actually, before I go on, let me just stop and ask questions or comments about the basic adversarial idea. Just out of curiosity, who here has heard all this stuff already in some other class? Be honest. A couple people. All right, but not everybody. All right, that's good. So I'm teaching, so yeah, you guys have heard this, I know. All right, so let me talk about an improved kind of GAN, right? So again, just a reminder that this GAN was like around 2015, sorry. A key adjustment was what was called the Wasserstein GAN. So, and I think that most GANs that you find are going to be kind of variations on this idea. So this was proposed by Arjovsky et al. In 2017. So again, this is only like, what, 5 years ago, right? So to me, to you guys it seems like ancient history, right? But to me, this is all still like very fresh stuff, and it's amazing how quickly all this kind of took off, okay? And again, just as a reminder, all of the papers and stuff I'm talking about for the most part, so here, the chapter in Foster that covers GANs is number 4, and then here are like the 3 papers I'm kind of talking about right now. The original GAN idea, which was, I don't think, demonstrated on images, but more like demonstrated on data. And then the DC GAN was 2016, the Wasserstein GAN is 2017, okay? So what are the kind of key ideas here? So first of all, they changed the loss function, okay? So, key changes. First is something called the Wasserstein loss. Could be Wasserstein loss, I'm not quite sure on the pronunciation. So there was a slight change just for making this work, that instead of having the discriminator output 0 for fake and 1 for real, so instead of the labels being 0 for fake and 1 for real, there was a slight change so that we use basically -1 for fake and +1 for real. Okay. The other change was that instead of the discriminator producing a probability or a number between 0 and 1, we replaced the discriminator with what's called a critic. And the critic produces a number that could be any number between -infinity and +infinity, with the idea being that real images should generate a big number and fake images should generate a small number, right? So the discriminator is turned into what's called a critic. And this number can be any number that I want. So in some sense, instead of interpreting this as a probability, we interpret it like just a score. So this is like some sort of a score function. You'll see that used, with the idea being that a big positive number should mean that things are real, and a big negative number should mean that things are fake. So I no longer have to constrain my discriminator output to be in this 0 to 1 range. Now that number could be anything. But I do want it to be positive for real images and negative for fake images. Okay? And so that changes the cost function a little bit, right? So now under this scheme, we have a very simple new idea for a cost function, which is that, what is that beeping? Hopefully not something that's going to be like a fire alarm or something. So the Wasserstein loss function is a lot simpler, right? It's the average over the training samples of yi times pi, where again, this is the true label, which is +1 for real and -1 for fake. And this is the critic output, which is, hopefully big plus for real, big minus for fake, right? And so the idea is that, ideally what I want is that real images is a big plus times a 1, and fake images are a big minus times a -1. And so before I take this negative, this is a big number, and then I want to minimize this negative of this number, right? And so a little bit easier to interpret. And then if I were to interpret it kind of like in the same kind of probabilistic framework that we talked about earlier, so minimizing the loss function is basically like saying, if I'm just talking about the discriminator or the critic, I want to minimize over the discriminator parameters the expected value of, this is like the discriminator applied to real output, and this is the discriminator discriminator applied to real input, and the discriminator applied to fake output, right? So remember that ideally I want this to be, big for this, and I want this to be negative for this. And so when I add these things, when I take the minus sign, this should be a big number, and negative, this should be a small number, right? Another way of thinking about this is that I want to force the discriminator outputs for real data and fake data to be as far apart as possible, right? I'm trying to push those labels, or not labels, I'm trying to push those numbers from the critic to be far apart on the real line, right? So basically the idea is that, I want to make these as different as possible. Okay, so hopefully that makes sense. And then again, for the generator, right, the generator has the kind of same idea as before. It's trying to fool the critic into making the wrong label, right, the wrong choice, right? So this is for the discriminator. For the generator, the cost function, again, is pretty natural, right? I'm trying to minimize over the generator parameters this thing. This is like saying that, we want, I want the G fakes to have big, positive critic values. Okay, so that's kind of like the basic idea behind this new cost function. Hopefully it makes some sense. Okay. Now, one kind of comment that, about neural networks is that neural networks are not really good with numbers in their, system that can increase arbitrarily, right? And there's nothing that really puts a constraint on how big the critic outputs could possibly be, okay? So that's why we use things like sigmoids and softmax and kind of things like that try to bring numbers back into some reasonable range, right? That's the whole point of something like a sigmoid or a softmax. So kind of what we need to do is provide some way to make sure that these loss functions are kind of reasonable numbers, right? So for that, we require a special condition on the critic's outputs, which is called Lipschitz continuity, okay? So if anyone has ever taken like a higher level mathematics class and optimization like that, you may have heard this word Lipschitz, especially if you have taken like a kind of control theory class. Sometimes you'll see that word used. So anyone who's doing like controller robotics, maybe at the graduate level, might have heard this word before. Not super important, and it's actually, the concept is really pretty easy. So to keep the loss values reasonable, we require that the critic be what's called one Lipschitz continuous. Which, in a slangy way, it's not exactly the same thing. It's kind of like saying that the derivative of the critic is bounded, right? This basically is saying that, let me write it here, that the difference between critic outputs over the difference between critic inputs is bounded like this, right? So in some sense, you can think about this like saying this is the average pixel difference between two images, and this is the difference between the critic scores. And I'm saying that you can't get too big beyond, so basically it's saying that the difference in critic scores is proportional to the difference in image scores, right? So in some sense, this is kind of like, in a slangy way, d prime of x, right? This is like the way we define the derivative was I take a little step in the direction and I divide by the step I took, right? So it's like kind of saying that the critic is got a bounded derivative no matter where I am, right? So this is true for any input images x1 and x2. Okay, so this is basically like a limit on how fast the critic outputs can change. As a function of the input. And so one way that we can enforce this is kind of like by penalizing the gradient from being too far from 1, right? We're trying to add an extra function to the cost term, an extra term to the cost function that says, hey, the gradient of your critic can't be that far from 1, right? So for example, what I could do is to say, okay, and this is the way it actually works. So here's kind of a bigger picture of the way the whole Wasserstein GAN works is that I take noise, I put it into my generator. This produces a bunch of fake data. And then I have a bunch of real data that comes from somewhere else. And then, again, I put this through my discriminator. I put this through my discriminator. Here, the answers should all be, big scores, right? 3.2, 4.3, whatever, right? And my goal is that these should all be, positive, right? Or maybe goal is not the right word. Truth is more like it, right? Conversely, the discriminator here may be producing a bunch of negative values with the truth here being -1 labels. Okay. And so here, there's basically a loss on this stuff and a loss on this stuff. I add these together to get the output. The twist is that the Wasserstein GAN goes through an extra step where I take some real data and some fake data, and I kind of make some what's called interpolated data. And I put that through the discriminator. So this interpolated data, is going to produce all sorts of whatever type of, outputs. Could be anything, right? But then I can use this kind of interpolated data to estimate what the gradient is for the current discriminator, right? So here, there is basically like a gradient penalty that gets added to the loss, right? So the idea is that, the middle branch tries to penalize gradient from being, too far from, or the absolute value of the gradient from being too far from 1, right? Maybe the norm of the gradient is a better way of saying it. And so the idea is that, this stuff here is kind of like randomly generated in the middle. It doesn't really matter whether they're good images or not. The main thing is just like providing, some source data for the gradient to be estimated kind of everywhere in the sample space, right? Because, here, you wouldn't necessarily learn as much from just looking at the gradient on only the fake images and only on the real images, because those things are supposed to be far apart in the first place. What you kind of want to do is generate some mixed up images in the middle just to see what the discriminator is going to produce, right? And so this is just for sampling the gradient, okay? Now, there are like a zillion under the hood making this work kinds of steps for this particular GAN, right? And so, for example, one thing that I read about here is that, we have to, in this case, train D to almost convergence before taking a G step. So there's lots of how does this really work, okay? Now, let me just show you some results that we cooked up in the lab earlier. So going back to our workbook here. So here, this is a Wasserstein GAN. Again, this is on the FACES data set that we kind of talked about at the end of the VAE lectures, right? And so here, again, we have these celebrity faces, right? These are the real images, right? We build a, generator and a discriminator, which again is for more or less convolutional neural networks on both sides, but we're using the Wasserstein GAN function instead. So here we have the Wasserstein loss metric. Okay, you can read the details in the notebook yourself, and then we start generating. So this is actually starting from an intermediate point. So probably more realistic is something like this, right? We start generating, and doesn't look like anything, right? It looks like random noise. But it doesn't take too long for the GAN to start producing things that look kind of facey, right? So if I scroll down a little bit, maybe I need to go a little bit more here. Let's kind of go down, drag it. Right, so now this is 129 epochs in. We're starting to make things that kind of look a little bit better. And if I scroll down a little bit more, now I'm getting things that definitely look kind of like blurry faces seen through a shower door or something like that. And so here, these are faces that are kind of coming out of having trained the GAN for, I would say about a half an hour, 45 minutes before class, right? So definitely these are starting to look more like faces. I mean, they look kind of like terrifying faces, but they are looking like human faces, and they definitely look, in places a lot sharper than the VAE results, right? So there's blurriness kind of in the backgrounds, but the facial feature parts are looking pretty good, right? And so here, I keep on training, and I have some sort of like weird error in my notebooks. So when I get to the very end, it's going to give me an error. But then once I've trained the network to a point that I'm happy with, then I can ask for it to generate new, faces down here, and I can make these samples, and this one looks pretty good, modulo the background. Some of these look like horrible mutant faces, but there's definitely a lot of promise, right? And again, this is something that I did on a modern computer in let's say 45 minutes to half an hour, right? And some of them are good and some of them are bad. And again, you can see kind of like here that all these are basically generated from the seed of normal vector, right? And I believe that if we look at the z dimension here, go all the way back up here. So the z dimension is 128, right? So that's like saying that we took a 128-dimensional noise feature and turned it into these 64 by 64 faces, right? So with a little bit more training and maybe a little more attention paid to what my cost function is, I got pretty close, right? So I'm hopeful that when you take your data set that you use for homework 1, that you'll be able to get something that kind of resembles this for the, for the system, for the images that you have, right? So we'll see what happens. And again, this may not necessarily even be the best way to do it, right? So this is like, again, a simple, like 2017 idea, right? But it worked pretty well. So yes, question? Can I go back to the, yes, what do you want to see?
Why are you assigning beta 1 and 2 twice?
I didn't write this. Yeah. This is just the raw notebook that came with the book, right?
Right.
So you can look into why. So you're asking about like, why is this?
Assigning it to like there and then in the end as well.
Oh, here.
Yeah.
Oh, well, this looks like probably is just a programming error.
Yeah, I can see it.
Yeah. Yes, don't take everything that you see here as something that I know anything about. But yes, so just again, this atom beta refers to just parameters in the optimization function, right?
So I remember, like in the original paper of the Wasserstein GAN, they were using the SGDs on that.
In the original paper of the Wasserstein GAN, they were using
The
stochastic gradient descent. Let's take a look. Uh-oh. Hold on, have to download it. So let's see here. So again, this is a case where, if you just read this paper from the get-go, you might not kind of totally understand its virtue. But let's see here. Experimental results, mixtures of Gaussians, loss metric, where we see what the actual, here we go. So this is basically saying that atom, is not great. We switch to RMS prop, it says. Yeah, that's the original one at least. Yeah. So again, your mileage may vary in terms of what makes sense. The other thing I wanted to say as a side note is that as you can see actually in the some of these outputs, especially like over here, like there's also kind of like this characteristic like checkerboardy look that, again, people have kind of proposed ways of using different loss functions, different normalization, and so on, to make the internal images look better, right? So again, I don't want to dwell too much on all the little nitpicky details about how this was refined. I'm just trying to get you to understand the basic big picture, okay? Okay, before I take more questions, let me just say one more thing before I kind of end up, which is that, so far, everything that we've done here has been taking a single batch of data and then training a network that can basically draw samples from the same distribution. But of course, what we're really interested in the future is being able to generate what are called like conditional distributions, right? So if I tell you, okay, I want to generate cats, I want to draw from the cat distribution. Or I want to generate dogs, I draw from the dog distribution, right? And so this is what's basically called like a conditional GAN. So, initial steps to controlling the output is kind of what's called a conditional GAN. So suppose I want to try to generate, dark-haired people versus light-haired people, right? If I just draw randomly from the latent space, I don't really know what I'm going to get, right? And so it's a very simple modification to say, okay, if my data is somehow labeled, right? For example, what I could do is say, okay, I've got my noise as my input to my G, but also what I provide is kind of like a new input, which is like a one-hot label, which is just something that's kind of like, a vector where only one of the inputs is 1 and the rest of them are 0, right? So for example, I could have this vector be something like, glasses versus no glasses, right? And that also goes into the input to G to produce an image. And then in the same way, the discriminator has to know what the desired label is too, right? So if I have an image, put that through D to get a score. In the same way, I also provide this one-hot label. Well, yeah, that's fine. And so this extra information that we provide about what kind of features we want the input, or we want the image to have, is something that then can guide the critic and the generator to produce things that are kind of like class specific, okay? And so here's an example, again, from the book where this data set of celebrity faces has these attributes. And I think that the one that they used in this case is blonde hair, right? And so what they use is just a single label. So it's basically like a one-hot label. And then kind of what's happening here is that the generator is creating a bunch of label equals 0 and label equals 1 images to see how we're doing. And so in theory, as this converges, what we should see at the bottom of the notebook is, kind of like dark-haired people in the first row and blonde-haired people in the bottom row. And of course, this network, I didn't have time to train to convergence. But if I did, so here you can kind of see this like an output where I think we could agree that on average, like the faces in the top row are darker haired than the faces in the bottom row, which have the blonde hair attribute, right? So that's kind of the idea. And so that's something that I'm kind of curious to know whether or not in your own data you can find some sort of attribute like that to do kind of like a conditional, generation on, right? Okay. What else? So again, these images still look, they look sharper. No, not these images, but like these images, right? So, we're definitely getting to sharp images, right? But they still wouldn't fool anybody. And so what I want to talk about in the next lecture are some of these advanced GANs that suddenly, number one, made the jump to much larger outputs, right? So being able to make a like 1024 by 1024 output is what we eventually want to do. And images that can really fool people, right? So the images, for a long time, and I'll show this next time, but I guess I can do a preview here. So just as a preview, you may recall that around the turn of the decade, there were these websites like, this person does not exist, right? And it would make immediately, upon reload, a super realistic human face, right? This is all based on, this style GAN that we're going to talk about next time, right? And certainly now this is the realm of being able to really make photorealistic pictures. And of course, every once in a while you'll see something that's kind of glitchy in these pictures, but for the most part, especially like, stuff that is not part of the face over in different parts of the scene. But for the most part, these look, pretty good in the face world, right? And that's where now things kind of start to get a little bit scary. OK, so let me pause and ask any questions about GAN type stuff. Basic idea. Yes?
Is there any quantitative assessment or metrics used to select the best model during training?
Quantitative assessment about how to select what for training?
How to select the best model during training? Because currently it's more or less like visual perception, like which one is better.
Right.
Is there any alternative quantitative way to do that?
Well, I mean, that kind of comes back. The question is, like, how do we choose the best stuff for training? How do we quantitatively assess how we're doing? That kind of comes back to the image quality metrics from last time, right? In some sense, the image perception quality, right? And one thing I didn't address here is, perceptual evaluation of the results, right? So to kind of go back to what we talked about last time, what I would do to assess the GAN would be to take an ensemble of results, and I would evaluate, in terms of a, it depends whether I'm doing like the full reference or the no reference, right? I could say, I could, they could look at the ensemble of results. I could evaluate, is there diversity, and then is there, kind of like quality, right? Another thing that I could do is I can take real images, and we'll talk about this a little next time, and project them into the GAN space to see whether or not the GAN world is able to well approximate what's going on, right? So I'm not quite sure that answers your question, but I think that generally there's not a lot of critical thought about curating the input data set. And actually that's something that I want to talk about very briefly, which is that when we take a data set like Celeb A, for example, that has these attributes, some attributes are unambiguous and kind of like, inarguable. Like, is someone wearing glasses or not is not something that you can have an argument about. But there is a whole history of image labeling in computer vision that is very problematic, right? And so what I would encourage us to look at is, so there are a couple of papers I put here, right? So one is basically the very famous paper called ImageNet, right? Is where a lot of these kind of like general categories of people and stuff came from. And initially, ImageNet was not really made as a person, generating, the goal of ImageNet was not to do a good job of classifying whether an image had a person in it. It was like, does this image have a cat or a dog or a house or whatever, right? But, ImageNet was kind of, not super carefully curated at the time. And so while it definitely pushed the field forward in terms of machine learning, also it was a big problem in terms of when people started to dig into the categories of ImageNet, there were some really problematic categories that were not well defended. And so actually, if you want to learn more about this, there's this post called, or this page called Excavating AI by Kate Crawford and Trevor Paglin, which is kind of all about, once you start to like browse the ImageNet categories, you realize, and again, this may be triggering for some people, which is I'm not going to go into it too much verbally, but there's a lot of stuff in ImageNet that is like, just terms and words that shouldn't exist, right? And then also just pretty arbitrary assignments of like, a guy holding a beer to a drunkard or something like that. And there are a lot worse examples in ImageNet, I can tell you. To the point that at some point, they were forced to basically remove all the pictures of people from ImageNet to avoid any sort of problems, right? And so, again, this is kind of getting at the intersection of, where these data sets come from and where the labels come from, right? That's why, I asked you on this homework to make your own data, right? To be intentional about what data are we putting in, so you don't have to worry later about taking problematic data out, right? I'm kind of looking for you to have ownership over your data, where you actually know every image that you put in there, and you can tell, oh, this one didn't this one didn't render very well as a sample because it's a little bit different than all the rest of the ones. I know when I took that picture, the lighting was bad, the angle was bad, the color was different than all the other ones, right? So I want you to have some sort of like sense of ownership. I don't think that when they created ImageNet that anyone really like looked super carefully at the labels in the data, other than just they slurped it all up and they started to have to throw out bad labels, right? But again, that was all done, I think, by anonymous mechanical Turkers in some country we don't know, right? Like, it's problematic. And I think that, computer vision has to kind of cope with that. And of course, when we start to talk about the future of generative AI, where people are saying, okay, well, authors are suing, large language model creators for having all of their fiction slurped in. And painters and artists are saying, well, you took all my images and used it to train Stable Diffusion, right? There's just a sense of like people are generating data sets that they don't really know the provenance of and they don't really care, right? So we'll talk a lot more about that as we get into the language model stuff for sure. And when our guest speaker comes to talk about legal challenges to generative AI, that's part of it too. But kind of it all starts with these big data sets like ImageNet. And so this is a very interesting article that I encourage you to take a look at that talks about, like why, how it all came about, right? So between this article and the Emily Denton article, I think that you'll learn a lot about kind of like the underbelly of computer vision. So I encourage you to take a look. Okay, so other questions or comments about Intro to GANs? All right, so let me stop the recording.